So in terms of presentation, so for any of them, of course, we have just have this kind of a background. So I won't talk about this too much because as we are in this project, all of us are carrying out this renewable offshore, and then we know this background. And just recently, you know, this kind of renewable policy in Europe, carbon neutral by 2050, in the UK, net zero, or in China, and they want to peak this emission by 2030, or also carbon neutral 2060. So that's our motivation. We always talk about these motivations. This reason we are carrying out, you know, this renewable, particularly offshore, as the main power source. Okay, so in terms of the comparison onshore, offshore, we all know that's the benefits of the offshore, and also the challenging of the offshore in terms of you know, this environmental or this harsh the circumstance and the remote area. You know, the offshore power installation. I just pulled out this data, and you can see in 2020, the installation this year is about 6 gigawatts. Is about half in China, and then the other leading country, UK, Belgium, Germany. This in the 2020 year alone. We can see that's the steady growth in Europe and then around the world. The accumulated installation, by 2020, around 35 gigawatts, and then according to the different data and estimation, about 2050 is 1,400 gigawatts around this the data, more and more, of course, for this project. So we can think of, you know, just imagine this one of the case in the next 20 or 30 years. Could we have the all renewable power based power system? So offshore is the one of the main source, and then plus the other technology, PV, and also hydrogen, and supported by the energy storage battery, because that's the to stabilize. Once to achieve the smooth and the economical operation, because the generation, if generation is a variable or intermittent, and then the load, although, you know, through the smart grid or demand side management, we can try to manage this demand side or load, but basically load is out of our control, is depends on the customer. So how to put them together, that's one of the overall question. In 20 or 30 years, can we achieve that power system, or renewable based, or power electronics interfaced? So you can see also in terms of statistic, in terms of generation, at the moment, of course, UK still has the most installed offshore wind power. The annual electricity generation about equal to 20 million cars. You know, this kind of load demand. If you had this one, so equal to this load demand, and then if we offset using the renewable power generation, offset the power, offset this conventional or thermal or the fossil fuel. So that's the contribution to the carbon emission reduction. You know, that's the number. So 62 million tons for carbon emission. So I put this total installation, installed capacity by 2020. So in the UK 10 gigawatts, China about also 10, and then other countries. If you look at this graph, the increase, you can see this blue one, this whatever the blue light, green, this is represent the UK. This China. So China still has the so faster increasing. So going to be the UK at the moment has the highest total installation in terms of offshore, but China also has the fast increase in terms of the installation. The green one represents the UK and the other Europe country. We have this resource, so we transmit the wind power to the grid. Even in our group, we have done lots of research. Even for you as a research, you have done 3 years or longer on this different technology, particularly the DC transmission. Conventionally, we use AC for the near coast, and then in some of offshore, not just for integration of renewable, but for the integration of different country, LCC, even within UK, the West Coast Link, that's LCC HVDC. But we know that that's if we install it in the offshore, it's almost impossible due to this large footprint size and required for the filter and the device. And also because LCC needed the AC source in order for this startup or the operation for the commutation. VSC, that's the we're doing. We know that's the reason why we put VSC, and also hybrid converter. I think in terms of this concept, this can be combined with VSC, LCC, combined with even for the VSC, the MMC half bridge or full bridge, and multi-terminal, and also even some kind of multi-terminal is not the different pole. So one pole in one location, another pole, positive and negative poles are different locations and using different technologies, collecting onshore, offshore. Fractional frequency transmission, that's the Giovanna has been doing or has done. Although according to her study and then comparison, this doesn't show the much benefits. I mean, overall economic and technical benefits. I suppose because if we use the fractional frequency, we need the converter anyway, and then it's still the AC. So converter already increased the cost, and then we use the AC and then lost some benefits of the DC. So overall motivation for this kind of frequency, for example, 1/3 of fundamental frequency, initially is the mature in terms of AC operation, and also avoid the use of DC circuit break. That's the motivation. We think that may or might present some of technical or economical benefits, but according to this comparison and then the summary so far, it's still not the competitive to others, and then this technology is not mature. Okay, so summary in terms of the advantages of VSH VDC. I don't need to repeat the reason. We all understand in terms of our project consortium. For this project, for this presentation, because we want talk about the collection system in the right-hand side, wind farm array. So of course this number is a particular number because I copied from the offshore wind acceleration. and but give us some general idea. If we have a farm, of course, conventional we use HVAC system connect to the onshore grid. Of course, this example is national grid, but I mean onshore grid. If it's close to near the coast, and then we use this AC system, and then if this is beyond the break-even distance, we use DC break-even, and then we need to convert this AC connection system convert to DC. I think this is the most that we are doing. So we use a conventional connection system and talk more on this DC, different control, different modeling, topology, protection, and the economic fee. This planning, this kind of research. This, I mean, number 3, if we use the DC, of course, now this we are talking about why do we use the DC in this presentation. We can discuss together, but then convert to AC. You know, it is kind of a combination. If we use the DC and then connect to the AC high voltage, so that's the option. Or we have DC, we step up this DC to high voltage, so DC and then connect to DC. So that's also the option, and then use the MVDC, medium voltage DC, and connect to the onshore grid. So this is, I suppose, that's also for certain distance or certain power range. We have already seen some of the study from Carbon Trust funded project, and then they talk about this kind of technology, or they talk about MVDC, but actually MVDC all the way to the onshore grid. I think that might be one of the feasible technology, because we know the DC, and then in terms of the distance and in terms of the power rating, so we connect them to directly to the onshore grid. So you can see, according to the combination AC AC DC 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 AC, all these things, this is the kind of mathematical combination. But for us, give us the opportunity in terms of academic research. Which one is the best or optimal or most feasible one? So I think that's the in terms of the cost, benefits, reliability, and then the availability of the device. So we need to bear this in mind. How do we select? But we know that's the some of the options. So if we talk about the DC connection system, of course we can get lots of idea. Also, inspiration from the existing AC connection system. We need to understand the AC and then try to extend, because some of the operation experience, existing device suppliers, even operators, they have already experience on this AC operation. If we can talk about DC based on the AC, make that more acceptable. In terms of voltage level, currently I think it's many in the 33 kilovolts or 66, okay, kilovolts in terms of this voltage level. But of course, some variation. That's the in terms of the connection system. So we put this in the medium voltage level. Okay. Connection overall, that's the for AC. So most, of course, that's the we call the parallel shunt connection parallel. So there's two typical topologies. The one is the radial topology. Another one is the star. If you look at this graph, gave us the clearer idea. That's the most of the offshore use this kind of configuration. you use the radio configuration or topology, and then it just has the features: low cable cost, the cable connecting them in a different string and connected to the to the hub, and then the control is relatively simple. In terms of reliability, of course, the cable size that might be different, depends on this the number and the rating of the turbine. The reliability means if there's a fault in some point, the downwards, all the wind power downwards could be lost. So that's brings low reliability. If we use the star, you can see in terms of connection. So each one actually is kind of independent. So each wind turbine, they connect to some connecting point. If there's a fault, so it only disconnect this particular wind turbine, and without affecting others. Okay, that's the initial. I think that's the initial motivation. So we connect this star. But of course, always there's some trade-off between the technology and then the cost. This require more circuit break, for each of them if there's a fault. So we need to isolate. For this radio topology, if there's a fault, so we don't have to. We can, but we don't have to install the circuit breaker everywhere. Although we can. So if there's a fault, only this here, and then we lost this downwards 3, or even if we don't install the circuit breaker here, so we lost the 4 or some of them. So we can put the different section, and to minimize, or I cannot say minimize. If minimize, we don't need any. We just put 1. That's also one of the operation, just 1 circuit breaker. So we can optimize, okay, in terms of the maximize the or balance of the power generation and the cost of the cable and the circuit breaker. So that's also this comparison. But for this one, we have to install. If there's no install and there's a fault on the cable, and then still all of them has to be shut down. Okay, that's the we put the different configuration in terms of the AC. So that's the configuration, the switch gear the requirement. That's the implies the higher cost. And then for the radio, of course, if there's a fault, we have already discussed that if there's a fault, and the wind power, some of the number of wind turbine has to be shut down. So if we put in the loop connection, either using contact to form the loop, or 2 string form the kind of closed loop. If we have fault, and then we only isolate the this section or this wind turbine close and then reclosure. So during the normal operation is the open, and then during the fault, we have to reconfigure this connection, this topology. So overall, the reliability is increased because we can minimize and reduce the loss of the generation subject to the fault. But this require more complex control system, okay, and also this reconfiguration needed this switch. Of course, this in terms of control might be difficult to manage this control or reactive power. This increase the complexity. So again, which one is better? Because this is some of the option. So we still need to balance the overall wind power generation, and then the loss of the wind power and the cost of the device. Okay, so that's the for the AC. So how can we or how can we use this for DC? For the DC, I think this motivation for the DC, I think, is the same as the DC transmission. You know, why do we use the DC? Initially, we use the DC because of with the increase of the power rating and the distance, and after the break-even point, break-even distance that point, and then DC can show the benefits because they require less the contact required, less space, also the power losses. You know, if we AC, we have to have the reactive power, and then for the DC, we don't require any reactive power and make a full use of the contact. And then for the DC, of course, the DC voltage rating for the same contact can be higher due to this insulation requirement. I think that's the this kind of technology motivation is the same. But in the past, we know that break-even distance generally for the overhead line, you know, hundreds, 800, 600, thousands kilometers. For the offshore, 50, 100 kilometers. That's break-even. So according to that rule of thumb, okay, we think, okay, yeah, for the connection system is only several kilometers or 10 kilometers or within that wind farm. So, you know, without further comparison, we know that might not be feasible. Okay. But with the increase of the power rating, and particularly also the power rating of the wind turbine, you know, before it's 1 megawatts, 2 megawatts, 3, 5, 8, 10, 12, 15. So more and more higher and higher power rating. That you know, and the distance between wind turbines and the, you know, between the towers and distance of using the cable also increase. So that might bring this question. I think that's reason. Another reason is, you know, higher reliability requirement. You know, in terms of this the control, or if anyway we have already used because of the grid code requirement, we have already used all the power electronics, and typically the wind turbine converter use the AC, DC, AC. The DC voltage is already there. Why can't we collect them? And one of motivation is so we can remove one of this DC to AC, that inverter. So that's the initial motivation. So in this case, we have this academic or research question or tech engineering question. Is the DC feasible or competitive? That's the reason we need to cover this topic. Although so far, of course, there's no DC connection system in use, but from us, from DC, we want to push forward, not to push forward of this particular technology. We want to push forward, you know, to put forward more options and then justifications for the customer. I mean, for manufacturer, for operator, for the government, for them to, you know, to make a decision. So we want to make this kind of contribution. So although so far we cannot say the DC is definitely better or worse in comparing to the AC. So we want to carry out this investigation, and also in some of research organizations in the UK, in Europe, and also in China. They are talking about they want to try or to demonstrate the benefits. We know there's benefits. We know there's also drawback, particularly in the economics and also the maturity of the device and some of control technology. The benefits also, you know, including if we use the DC, and then we can reduce, because in the offshore, we can reduce the size of the transformer. Okay, that's the all these these factors we need to take into consideration. About how many years? 5, 6, 7 years ago, or even 8 years ago. So we also work with visitors from UPC. So we investigate the variable frequency in the offshore connection system. So that might be above 50 hertz or lower than 50 hertz. And in some of the comparison, we found even 32 hertz. In that case, 32 hertz was in some cases, or 30 hertz sum of frequency is one kind of optimal solution in that particular case. So if we add this DC together and for different case and for different size, distance, and then voltage level, so we need to consider that and in our analysis. So we have all these questions and motivations. So we want to demonstrate and also contribute to overcome the technology difficulty. So I copy this graph, just to show this generation wind turbine, and then that's the connection system. If we can use the DC connection system and then connect to the transmission, this is also represent the DC and some component, of course, turbine, the switch gear, circuit breaker, cable, protection. So that's the basic technology required for this connection. If we're now in this presentation, so we want to cover this part, and then if we connect this all the way to the onshore or use the AC or DC, that's the transmission level comparison. Configuration, topologies, DC connection system, and this one is the parallel, because you can see if we recall what we discussed about the AC, that's the radio and also star, and then for the DC, this most use this radio topology for the radio, and then for this configuration, if we just have a DC output, we use this to represent DC output and connect it. This is a kind of parallel string connection, okay, in parallel, and then we connect to the transmission with the DC-DC converter or platform. So that's the parallel, because that's no voltage to higher DC or AC voltage. We just give you the sum of information, because we found in many documents when people talk about the DC connection system, they mean the DC radio. So with the DC radio, and that means the parallel, okay, because the DC parallel. The reason is, according to this configuration, we could have a star. We could have star, but just now we have already analyzed. If for the star connection, we need a circuit breaker. AC circuit breaker is mature technology, although it increased the cost, but anyway, it's mature. For the DC, if we install so many DC circuit for each wind turbine, and with the one DC circuit breaker, so that's the significantly increase the cost and the size. I mean, we so far we know this DC circuit breaker, this very large volume, the size. So, and then for the medium voltage size, what's the suitable DC circuit breaker? So we need to further investigate. So that's the reason people so far don't talk much about this star topology. So this DC radio, they mean the parallel. Okay, so this for us, we just clarify this definition. Okay, because they have avoid or omit this star topology. But who knows? Okay, in the future with the increase, I mean, improvement of the technology and decrease of the cost. DC circuit breaker. This DC circuit breaker do not have to be as the HVDC circuit breaker. That is a mechanical, hybrid mechanical, electrical, that kind of circuit breaker, and then this main branch or that kind of sense, and make the very huge. We can use some other technology, might be feasible. So that's, we can still put here as a general we can still put this as an option. We don't want the company to remove, and then with the changing or development of technology, who knows, this may become an option or competitive again. Okay, another one is this cannot be achieved in the AC connection system is DC series topology. So if we use this one to represent the DC wind turbine, and then we connect it to in series, okay, to form the higher DC voltage. You can see if we form high DC voltage, we can remove this kind of platform, remove this DC converter, and then form the DC voltage, and then you know, just link to this point to form the HVDC. So the DC output from HVDC. Okay. That's again is motivation, and then some of the benefits we can naturally think about. You know, increase the voltage and without without need this kind of transformer, DC transformer, and then also reduce the platform. That's the huge saving in terms of cost, in terms of the size of platform. Okay. Trade-off, compromise, always when we carry out this technology. And then in terms of the control, the operation, they couple together, and then if they connect in series and all the current is the same, and then when they connect, no matter if which one is a positive or negative pole, so one pole connected to the high voltage, some in the middle, some low voltage, so the potential and difference is very high. This brings the challenges in terms of the insulation. Okay, so different wind turbine have a different insulation requirement, and then those close to the pole requires the higher insulation requirement. Okay, that's the one of the problem. And another problem is because they are connecting in series. Okay, wind power that intermittent, so wind speed variable. So this power of each wind turbine are different. Although when we design the wind farm or the each wind turbines, when we form the string, kind of this string of the wind turbines, we try to connect them. One is close, one is the similar power output, and one is to minimize the cable distance. So we take this into consideration. So we cannot control, we cannot maintain all the power to be the same. So this same DC current, but different DC, different power means different DC voltage. Total DC voltage, if that's the fixed, so this voltage sharing, they are different and also variable. And this could cause the over voltage if one wind turbine has the high power, some others has low power, and then this imbalance in the power sharing and the voltage sharing, and could cause the over voltage, because total DC voltage is fixed. Normal operation, we fix them. So that's another challenge. Of course, when we talk about this is the one string. When we want to form the DC connection as the wind farm, it's not one string, so many strings. That's the series, parallel, and naturally in a wind farm, offshore wind farm, so it should be series parallel connection. Okay, to form to cover the whole wind farm. The DC voltage, they share these strings and series strings share the same DC voltage. This brings another challenge, because if there's variation of the power, and then but the DC voltage is the same, and they could affect each other. If we want to maintain this DC voltage, if we use this converter, onshore converter, inverter actually here to maintain the DC voltage, and then the power, and then the power output, voltage sharing, this bring the complexity in terms of the control. Okay. Okay, some people are very clever. They're very clever. You know, we have this this drawback, and then if also if the fault of one wind turbine out of service, and then the number of the turbines, they're different, the voltage sharing, they have to reshare this voltage, and then each one has to share the higher voltage. So that's the more problem. Okay, so people present some of the, you know, some of the idea. It's called matrix interconnection. So we use the other switches to connect them, interconnect this string, and then just in case they can connect in parallel or series, and in one of the in out of service we connect some other ones. This can solve the problem. Of course, obviously you can see the operation is so complicated, and need more switches, means the higher cost. Yeah, that's the some of the clever proposal in terms of the different topology. For us, we present here as a lecture or just a kind of workshop. So we put it here, and let's say maybe in some cases, and also with the development of technology, that might be become feasible. Okay, technology and the challenges. One is wind turbine. You know, DC. Initially, we know that if we look at the initial one is the wind turbine, AC, DC, and DC, AC. That's wind turbine. So initial idea, as we discussed, if we are already DC here, can we just use the DC and then put this as kind of a DC wind turbine? Okay, and then if they want to connect to the high voltage and use another DC converter to form the high voltage, or we use this wind turbine, many of them connecting in this parallel, and then use another or DC to form the high voltage. If we use this one to increase the voltage, actually we have this actually is contradicted to one of the original motivation. Do you still remember one of the original motivation to use DC is if we use DC, we can remove one stage of the conversion. But you can see if we really want to make this operation properly, and we sometimes we cannot avoid. I think this point is similar to many other DC technology application. Some in the building, some DC office, and DC building, DC community, all these kind of things. So we are here. We are all, you know, for this project, we are all there DC people. But I'm not saying we are always, you know, without any argument to support the DC. We will still need based on the technology and the feasibility study to think which one is the better or optimal. So if people just say, why do we use DC? Because we have a DC, we can remove one of the conversion stage, and the DC can connect together. So this is not the case for the photovoltaic. You know, some people talk about photovoltaic and then connect to the others because they are all DC, so we can connect them together. You know, DC 9 volts, 12 volts. Can we connect 9 volts, 12 volts together? Even in this DC office, we cannot. We still need some, you know, conversion. So we cannot always, you know, remove this conversion, either DC AC inverter or DC DC. Okay. So how good? What's the the basic reason, and then what's the cost? What's the benefits? We need to investigate case by case. And then some of the in order to increase the voltage, using the AC side to increase the voltage, and then use one stage of AC/DC rectifier, or other high frequency or medium frequency transformer in order to reduce the frequency, because if this is the 50 Hertz or different low frequency, and then the transformer size will be higher for low frequency, transformer size will be smaller for high frequency. So that's the some of option. And then also in terms of the safety issue, and then we need a galvanic isolation, and then we put this in a different we need this isolation, okay, and also use a different topology. So I think this work actually, I put here, this is the summary. This is the work Guyan doing in collaboration with DTU. Is that right?
Yeah, Professor.
Yeah. So I mean, this is some of work. Even we look at this one. If we look at this final one, F, whatever, this also contradicts to our initial motivation. Our initial motivation is to reduce. We have this voltage there, so we connect this voltage. We can reduce the conversion. We can reduce the number of converter or number of power electronic switches. But you can see we need so many stages in order to achieve safety, flexibility, and then this different control. So if you look at the configuration of wind turbine, you can see that's the initial three-phase rectifier, AC to DC. But then we need a different topology for this. We can regard it as DC-DC. DC. We need 12 more power electron switches, but benefits is we could reduce of course we can reduce the size of transformer if we increase this frequency. But if we increase the frequency, this cause the higher switching power losses. So benefits, drawbacks, and then the cost, and then the power generation. We need to put them together to have the overall decision. So that's you can see this what I always said in terms of the academic research is kind of a trade-off or compromise between different technology, or even between very good technology and the cost. Okay, so that for DC. So what's the best one? I cannot say which one is the best one. Okay, depends on the case and the application, and also requirement. If in some cases the control or the harmonics or some other combined with the other technology, offshore, the hydrogen, this kind of different technology put together, we form another generation of plants, and then might be some of technology might be used, and then in the offshore to achieve this overall optimum operation. Okay, so we know that's the many options, and then that's the DC-DC converter. DC-DC converter, that's for high voltage. Of course, if both sides is high voltage, we cannot avoid. We have to use the MMC. But for the medium sides, we have already carried out this one of comparison. For connect to the high voltage, so far we all agree we have to use MMC, but MMC has the half bridge or full bridge. But medium voltage, tens kilovolts, 10, 20, 50. So is the MMC still the best option for the medium voltage converter or transformer? this again, the initial question, research question is for wind turbine. Most of wind turbine is 2-level. Okay, some of wind turbine use the 3-level, even before three-level converter. And then for the HVDC, now we all agree use the MMC. In the middle, between 2-level to the MMC, in the middle, there must be some point. Okay, because very high MMC, very low 2-level. In the medium, in the middle. So which one? So we have to have a proper formula to determine to find this optimal point, and then to have this justification to identify to which factors, to determine our options and selections. Okay, this is some of the work in terms of medium voltage. In Cardiff, we are currently undertaking one of the medium voltage project in the North Wales, Anglesey DC. That is not offshore. That's the onshore distribution. 33 kilovolts converted to plus minus 27 DC kilovolts, and then in the project they use the cascaded 3-level. Okay, that's another option. Three level converter, and then cascaded. For each arm, they have 6 connected in cascaded. So that's also is their project, is their choice. But for us, for our research, so which one is the best? We need to determine, and more important for us is we need to find a way, a method for this determination, and also that is required for. General requirement for our project, InnoDC, is innovative tool. Okay, when we design this project, so we want to move this technology readiness level. So initially we have some academic idea for this project. We want to generate a tool for other customers, even for academics, for them to use, and then to represent our contribution. So the answer, not only answer, but also the way, the method to find the answer. Another technology, cable. I think that's the offshore cable, different type of cables. I think that's the available for the this medium voltage level. But again, cable and the layout the cable this incurs high cost, still very high cost, and then that's the motivation. We use the DC is reduce the use of the cable if we use the DC, and then make full use of the material if we use the DC, and then we don't need the reactive power, and with increase of the wind turbine, for example, 10 kilowatts, 15 kilowatts, and the distance, I don't know how long that's. 5 or 10 kilometers or 2 kilometers longer or further, and then with increase of distance and DC might show the more benefits. With DC, now if in terms of control, I think this idea we will understand because we are doing this HVDC. We know this different converter coordination and proper control based on this modeling, and another one is the fault. Okay, if we have DC, we have a fault, we have to identify this fault location, and then interrupting the fault current, and then isolate the faulty circuits. Although I put here 2 or 5 milliseconds. And this is, I don't think that's really the case for the offshore, because this the medium voltage. How long the if there's fault, and then if we don't interrupt the fault current or isolate the fault, they'll cause the very high fault current, and then lower voltage drop. And how long can these other components no matter this other circuit, converter, and then can withstand, and we need to identify this fault current is fault isolation time. For HVDC, we all agree about 2 to 5, and then sometimes if we use this MOS reactor or this inductor, and then this can be a little bit longer, 2, 5, 10 milliseconds. I think that's range. For the medium voltage, in terms of stability, I think this can be longer, because the low voltage, this disturbance is reduced in terms of low voltage. This is just the general knowledge for the power system. If the voltage is lower, and then possibly they can withstand longer fault before the system collapse. And also in terms of but during the operation, the current, DC current, if we have some of the converter, 2-level or some power electric converter, the capability to withstand fault current might be reduced. So this again might be require even faster fault identification or isolation. So which one? How long? We have to isolate the fault. Also, if we also compare the HVDC, if the HVDC, if there's a fault, and then why do we have this one? Because this also related to the customer. If we lost the power, huge power, 5 or 10 gigawatts to a system, and then for too long, and then this won't meet the grid code requirement. So they have to isolate fault and restore the system. Without notice of the customer, although they can notice some in terms of measurement, might be short voltage drop or voltage dip, but we don't want this affect the customer. But for the medium voltage, this side, this requirement might be lower. Okay, if it's a little bit longer disruption, because if it's not directly connected to the load or the main load center area, they might be okay. So I put this all together, means you can see even for this point, there are different requirements. Some requires faster, some can withstand the longer or slower response. So which one we have to consider again, case by case. Okay, so this in terms of fault protection algorithm, and then this requirement, if we require different protection method, communication or other device to identify the fault. Another one, okay, if we have already identified the fault, DC circuit breaker, we have already talked about the DC circuit breaker. Can we use the only solid state circuit breaker in the medium voltage? Yeah, maybe. Let's see. We compare to HVDC. For HVDC, the technology itself is okay. We can use pure solid state based circuit breaker. But what's the drawback? We are supposed to or to understand that because the power losses, that is not acceptable for the operator and the customer. If we only use the solid state circuit breaker, and then that's the reason we designed the hybrid circuit breaker. And for mechanical, that's too slow. Solid state, the high power losses. But for medium voltage, is this still the case? If we use mechanical, some of the mechanical methods may be slower to generate this current zero, but can this be acceptable? Or we use the pure solid state circuit breaker, or even some other medium voltage. Some are already available from the manufacturer. If the power losses, can we accept that kind of power losses? If because the voltage is not 400 kilovolts, it's only 40 kilovolts, so it's 10 times less number of IGBT or whatever, that's solid state component. So that's also we can we need to compare. Okay, so this the in terms of protection and then this isolation device. There's also some challenging. Other control, we have to achieve is the DC turbine. So we have already present and proposed this concept, DC turbine, also DC converter. How do we control and then to optimal to schedule the power and then reduce the power losses, and then also avoid the over voltage. For example, if we use the series connection. For the technology, this wind turbine, so this any stage wind turbine, of course, is mature wind turbine, and the wind turbine converter. So that's I think most a wind turbine converter. If we put this wind turbine converter, we need to think which one is the best one. Although if we look at technology itself one by one, I mean that's all mature. It's just a matter of inverter or rectifier. Okay, but in terms of the availability or readiness of all these components, this is switchgear. Yeah, isolator, or this we sometimes call it disconnector for the DC offshore. DC converter is still also in any stage. This research have been covered already many years in terms of HVDC application. But for the offshore, between medium voltage or between medium voltage and high voltage, and there's still lots of work to do. This circuit break, the cable, I think that's the okay in terms of this voltage level. So for in summary, you can say if you ask the operator, so is this the technology ready for use, or how they can think about this availability or readiness? I think the answer is the cost, is the economic. They only consider the profits. If we put this investment, the cost, can we get the sufficient profit and receive the payback, acceptable payback or payoff time? So that's the only answer for them. And then so for us, we have this requirement for the different technology: turbine, cable, protection, transformer. They all the sense. So we need to know, or at least at this stage, to estimate the cost, and then we know this initial for this technology and then device. We know that the cost is this component, and then during the operation, another concern is some of maintenance or failure, and in terms of operation, the power losses, energy losses and power losses. I mean here, energy losses is, for example, the curtailment of the wind power. We have 5 megawatts wind power, but because of the operation, we have to curtail to 4 megawatts, and that's the energy losses. And then that's sometimes I mention, this energy losses of the power from the power source. Another is some other power losses through the cable, through all these power electronics converter. Okay, this power losses. So that's also this kind of negative side. And then the positive side is the maximize the power generation and the power transmitted to the grid, because that's the electricity generated, and the operator can earn money, can make a profit. So they maximize the generation and minimize the cost and minimize the investment. So that's the economic analysis. And then when we talk about this energy losses and then power losses, and also energy losses related to this fault, because if we have fault, we have to isolate the fault, isolate the faulty circuit, and restore the unfaulty circuits, and then shorten the disruption time in order to minimize the energy losses. This is another reason to cause the energy losses. So if there's a fault, that's one thing, or failure of component, or sometimes need maintenance of the component. So all this reliability in terms of the cable, joint, the converter, turbine, circuit break, and even some other control circuit, secondary side circuit. So we need to connect all these data in terms of reliability to know their reliability, no matter it's 99% or 99.9 or 0.999%, whatever, have a different number. Some, of course, we cannot reach the 99.99%. Some device 95 or 98. But this is the particular device. Overall, we don't have for the offshore, because there's no practical system, and then we don't have a statistic data. So we need to cover using analytical method or some other mathematical method to estimate this reliability of each component, and then based on the different configuration, different topology, to analyze the overall reliability, and use the reliability to identify the overall availability, to identify this overall electricity can be supplied successfully to the grid. So that's the reliability analysis. I put the graph here is just say we have a different configuration. So, and then for each component, and then a series and a parallel, and then the failure. If the failure, how much wind turbine, how much energy could be lost. So that's the and then use the, of course, in terms of reliability mathematics and then algorithm, they almost mature. There's lots of, because they have already been used for the AC power system. This methodology, we can say that's mature. But in terms of the data, different operation characteristic, and how do we consider, the special features in terms of the wind turbine, or the between this different distance, or even some other wind turbine, for example, wake effect, and how do we analyze the this reliability, and eventually we all convert it back to this sum of the economic index. That's what we want, and then we can present, according to this comparison, we think which comparison or which configuration or topology is the optimal for which case. So maybe even our recommendation, maybe even just, okay, AC is better or best. That's the case. Okay, but if we can make our contribution in terms of the converter or new idea or new protection method, we can reduce the DC and make this more competitive. I just used this sum of result in our previous results. I give you the idea. I mean, according to our estimation in terms of cost, and then so if we compare just give you an idea, 5 kilometers the cable length, and then if this wind farm is 400 megawatts or 200 megawatts, and what we need to cover: turbine, wind turbine, DC or AC wind turbine, and power electronics, cable, platform, protection, and then circuit, and the operation, the other losses. So you can see for the turbine, the AC, and then for the DC, which connections DC2, these two, that's you can see. For this one, use the just the AC to DC, one conversion, and then connect from the lower DC voltage and use one DC convert. And this one, this DC connection system, suppose we have already used the AC to DC and another DC to DC converted to higher 30 kilovolts connection system. So each wind turbine has already consist of 2 stages, AC to DC and DC to DC. Okay, so that's the difference, and that's the conventional AC. So you can see the cost. So that cost might be turbine cost, of course, is lower. We remove that inverter stage, and this the higher. And then connection cable, we need to compare the connection cable, and then platform. So use this DC1, we have already formed high voltage, so we can reduce platform in terms of DC-DC converter. And this one, if we use the we need another separate DC-DC converter, so increase the platform. And then in terms of protection, AC more mature, and then the protection requirement is lower. DC requirement is higher. Okay, so we compare this overall in terms of the this device. You can see sometimes this is higher, this is lower, and this is higher, and this is lower. Or this kind of comparison, we put the overall and let's see which one. Also compare different size in terms of the wind farm. Okay, so using this data, you can see according to this available data and our estimation, DC is still requires higher cost. That for this one we don't compare this. This only compare this investment cost. Okay, for this table we haven't include the generation. So possibly if we use DC and then lower power losses, and in terms of the sum of the fault, higher power generation. But in terms of the investment, the DC is still higher. So that's the reason. I think that's the reason so far. There's no DC connection system in practical application. How do we move this forward towards this practical application? Okay. And of course, some of data is just based on the estimation. With the mature of the device and our technology, some data has been changing, and then this number. This is just for just for one of the example, and based on our assumption. So how can we move around this, and then eventually changing this conclusion. Okay. Do you have any questions or discussion? Do we need a break or just carry on?
I think we can carry on.
Okay, if there's no objection, we can carry on. Give me 10 seconds. I need to drink of water.
That's true.
If I ask a question?
Yes, please.
Regarding the galvanic isolation, is that really required? Because in PV applications already use non-isolated topologies. It's but if you use like the topology B, the other one, yeah, topology B, we could eliminate some components, but from the industry perspective, is that really required? That
so Kayan, are you asking the question?
Yeah.
Okay, so I think some of the work is the this undertaken by you, but I mean I can answer generally, because for the different topology and different connection, And then for the safety issue, these galvanic isolation are required. You know,
yeah.
We know we want, even for the PV converter design, we want to remove in order to reduce the cost and reduce the size. And you know, if that's the case, and then there's the security or safety requirement can be met. So that's the this reason we do not have to say we have to use, but in some operation you can say different configuration, and then who knows, in this offshore wind farm, and different connection and the form, and then changing or reconfiguration that might be cost, you know, in some cases, you know, this voltage potential problem.
Yeah.
The another one is, of course, that's for research. If for the series connection, you know, they have to use this isolation, because they use different potential. At different potential, if they share the common points, of course they cannot form the, you know, the strain of the voltage. And also, if the one converter is out of service, and the potential also changing. So that's the of course, even for this matrix configuration, that's too complicated. But I mean, in some cases, this might be required. Although our purpose, always the purpose is to, if that's safe enough, we want to reduce the size, and then to achieve this long isolated converter. This is true for the PV and the other renewable power generation.
Yeah. Yeah. Thank you. Yeah.
So for the case study, so I used the one of the research in terms of comparison or control of the series connection. Just to give you this idea what we need to cover, and to draw the conclusion or get some funding for this offshore wind farm operation. If we look at this configuration, series parallel, if one string, and we know that due to this variable wind speed and the variable wind power generation, the voltage, because the current is the same, so the voltage is variable. And then if this is unbalanced, and then the different power and the voltage sharing are different, and if the total DC voltage is fixed, and some of the converter could subject to the old voltage, and then how do we avoid? So of course, the very straightforward natural answer is, if we increase the, you know, the voltage rating for each wind turbine, yeah, that of course, no matter how much change we can withstand. That's the very simple answer, but I'm not saying this is the very feasible or optimal solution, because if we increase the voltage rating, means the cost of the wind turbine. And in most cases, most of the time, the rating is wasted. The rating, the voltage rating cannot be fully utilized, because the when we design, we suppose that they try to, in a close, approximately close the wind power generation. So that's the and then if there's some variation, so there must be some certain range in terms of voltage variation, and only in some extreme case, you know, there's extreme imbalance in terms of wind speed across, you know, through all these the wind turbine of one string. So that's utilization of the increased voltage rating is too low, and then the waste of the material and then the investment. So another one is curtailment. So if this, for example, the wind turbine has a higher wind speed, this is lower or this is lower, and then the voltage could reach the limits, and then we have to reduce the wind power generation, and then that means the loss of the energy. So that's the that's the question. So how do we solve this problem? And then when we solve the problem, we don't want to increase the cost too much. We don't want to waste too much wind power. And then what's the solution? Okay. And then in this solution, we have considered different wind speed, different topology, the power rating, distance. Okay, so but the overall question is, if we use the series and the parallel, so that's the challenge I have already explained. One is the over voltage in terms of experience the over voltage. Under voltage, some low power experience under voltage. That might be also the problem if we don't, if we just use typical converter configuration. You can say if the DC side that's too low, and that becomes uncontrolled the converter rectifier, because the DC voltage must be higher than the √2 peak value of the AC voltage. So if too low, could also cause the operation problem. So you can see this imbalance in terms of wind power, the cause problem if we don't have any further solution or consideration. And then minimize the Kt and minimize the power. So initial case is we compare the the different configuration. If we use the 10 total, how many? If for each wind turbine the output voltage is 30 kilovolts, and then if we want to use the 30 kilovolts to form the DC voltage, total 600 kV, and then we put this 20 wind turbine in series to form. Or this reduce the DC voltage, HVDC, this 4 by 5, 4 connected in series and 5 strings in parallel. So the 5, the 4, 1, 2, 3, 4 times 30 kilovolts each, so it's 120. Okay, and we assume this 1 kilometers, 800 meters, 800 meters, and this assumption. Okay, this we have this kind of base case, and then compare the use the typical wind speed distribution, and then we calculate. You can see here different wind direction, different wind speed, and then for this this power curtailment, power curtailed. Okay, under the total power under this different wind speed, different direction, because this direction also affect, because the wake effect. If all in the string, all the wind turbines affected in the same rate, and actually this won't cause any problem in terms of the curtailment, because if the wind speed increase, the oil increase or decrease, the oil decrease at the same time, and this is not a problem for this study. The problem is wind in a different direction, and then the turbine has a different speed, and also affected by the wake effect, and then the power, this will increase actually the power curtailed. So we analyze, calculate this power curtailed in order to maintain. We set the voltage limits for each wind turbine. I don't know how much is 10%, for example, plus minus 10%, and then if reach 10%, we have to curtail, and then through the calculation. Okay, for this one string, and then for the 4 by 5, the 5 strings, and on the different speed to calculate this power energy losses. I give this in terms of electricity lost, annual losses. If we look at that, some annual losses due to the wake effect, and then if this normal voltage, normal stream voltage, we don't change in this voltage. Another one is if we change in the voltage, reduce the voltage because this curtailment. And if we want to reduce curtailment, we reduce the DC voltage. This DC voltage by 20% or this by 20%. 25%, okay. By 25%. And then if we reduce, and then all the voltage won't experience the overvoltage. And then they make it safe. We don't need to curtail the energy generation, wind power generation. But we reduce the voltage, we have to increase the current. Increase current means increase the power losses. Another power losses along the this cable or some converter because current increase, and then we calculate all this, and we put them together. This curtailment, how many? This in terms of annual, this electricity gigawatts hour, and then this losses, and just put this data, and for the different cases, 20 turbine, 1 string, or 5 string, 4 turbines. And then if you look at this graph, I use this graph to summarize this data. This is only case study, okay, for this example. Energy curtailed, if we use a typical for this 20 turbines, use typical, we don't change the voltage. This is the energy curtailed, and then the blue one represent the power losses because the increase of this current through the conductors. If we reduce the voltage by 25%, and then energy curtailed has been reduced. Power losses increase. You can see this increase. The reduction is more significant than the power losses increase. This is the same for the this configuration 4x5. Okay, fix the voltage, fix DC voltage. The energy curtailment, and then if we reduce voltage, energy curtailment reduce, and then power losses increase. So with this comparison, you can see this curtailment is more significant than this curtailment reduction is more significant than the power losses, particularly copper losses, this kind of increase. So it means in this case, it might be feasible to reduce during the operation to reduce the DC voltage. We also compare the loss of turbine, because either due to the fault or due to the failure of turbine, and then the sum of wind turbine is out of service. Out of service, of course, we can bypass that turbine converter, and then the number of each string are reduced. Number of each strings reduced. If we use 20 turbine together, and if we lost 2, you can see our study is either lost 2 wind turbine, or another case, the right hand side is another, only 1 wind turbine failed. Okay, and then for different this topology case, and this assumption is, you can see in the series string, either there's the wind turbines with the maximum power failed, or wind turbines with the minimum power failed, because we use this extreme case and to get the idea. So you can see 2 lowest power turbine failed, or 2 highest power turbine failed. This is the 2 wind turbines. If 1 wind turbine, there's another case. So it's 1 highest or lowest, or 1 is highest. So we also compare these power losses, the wind turbine curtailment. So get this result. So the amount of power losses due to the string failure can be reduced. This for one of the string in that wind speed case. reduced, and then for this different power, okay, so lowest power and for highest power, the different number, because this and in the middle, in the in the middle power, and then that number should be between them. And this power, this failure, and this power curtailment can be further reduced by reducing this the DC voltage. Okay. So the DC voltage we tried for the 10%. We tried 10%. We also tried the 25%. This voltage reduction. Try to find the this comparison, which one overall compare this overall this cost. They minimize these losses, minimize the losses. Of course, in this study we have also covered the rating. Okay, yes. If we increase the wind turbine rating by 10%, so another way to avoid the failure is to provide over voltage of this converter. So for this one, this ratio, if we increase the this number or voltage number, 10. This is it's not 10%. This is 40, 100. Okay, yes. So for each one, because the each wind turbine is the 4x5, and the DC voltage is fixed 120, and then initially wind turbine is 30 kilovolts. And then if we increase the wind turbine voltage rating when we manufacture, when we order this component, this voltage rating is increased by from 30 to 40, or from 30 to 31, and then we can get the to reduce the power losses. Okay, to reduce power losses. So you can see, in order to this, we need also comparison. We increase the power rating in order to achieve this same power losses. So we have to increase the power rating in order to achieve the power losses. For different stream, this requirement are different. The overall, we haven't compared this cost. We don't have a very accurate data, but just give the indication. Indication is increase this from 30 to how many in order to maintain the same power losses or minimum wind power curtailment. But the increase from 30 to 40, what's the implication in terms of the cost? We don't put this number. We don't have this number, but we can, if from the manufacturer point of view, or if we have the sufficient data, we can carry out this comparison. Okay, this ratio, and then for each case we can have this comparison if that's worse. Although this operation, of course, this operation in terms of this series topology is still very complicated. We haven't considered in terms of insulation. Okay, that insulation design, that is also the factor if we do want to use that configuration. Okay, that's some of the findings from the case study. We have also covered, if this, you can see in that configuration, the distance is 1 kilometer away, and for stream between stream is 800 meters. If, and the wind turbine is how many? 5 megawatts. If that increase to 8, 10, 12, or 15 megawatts wind turbine, and distance increase from 2 or how many 5 kilometers each, depends on this the rating, and then we can use the same method to investigate the power curtailment and then to analyze the overall energy and power losses. But from this investigation using the method so far, we found reduce the stream voltage can reduce the energy curtailment. But these and also, yeah, this curtailment is greater than this increase of the power losses, converter or cable power losses. This is the one of the finding. Some others, this finding is also this might be okay. This might be some of the alternative. We have this option, and then we use this method. We reduce the size. Particularly this offshore platform, the converter, the DC-DC converter to step up to the high voltage, and that's I think it is huge reduction. And the main motivation purpose, we use a series connection. So in terms of curtailment, in terms of the power losses, in terms of the platform size, and also installation cost, that's need some further investment, investigation and a comparison. So that's the we just put this as one of the study case, and to try to should show these factors. Okay, these factors, and then if we reduce the voltage, that's in terms of operation. If we reduce the voltage, and then we can reduce this curtailment. But I think if it's operator, they might not like this kind of idea, because if we want to reduce the DC voltage, we have to control that inverter side HVDC from onshore inverter because that inverter to maintain the total DC voltage, and then they have to vary DC voltage according to the different wind speed and different direction. I mean, technically, it is feasible. That make this communication. One is the difficulty in the communication. One is the operation more complicated. Okay, so if at this stage if we present this kind of operation idea, I don't think the operator will like this. But if we can have a more automatic control, or based on, as we discussed at the beginning, based on this very good wind prediction, wind power prediction, wind forecast, and then based on the even big data analysis, we know which one we can make a quick decision, automatic quick decision that might be achievable. Okay, that's also some of possible research idea. Okay, yeah, I use the this DC connection system has already been proposed several years ago, and then some of opinion or insight or message, of course, was not generated by me, because some of the common sense, some of is under debate, and some of case study in this presentation case study I got it from Padma's work, and then from some figures from Guyang's work. Yeah. As I said, you are all supposed now to be the specialist in this HVDC or offshore wind farm. So I'm here is not to teach you. It's just to have some of useful discussion. Okay, thanks.